We've all seen those slick animations for AMD's 3D V-Cache, the tech that's just been dominating gaming CPUs. And it looks so simple, right? You just stack a cache chiplet right on top of the processor. Easy. But what if I told you there's a huge secret hiding in that simple animation? A manufacturing story that's way more complex and honestly way more interesting than we've been led to believe.
Yeah, that marketing animation? It's a very convenient simplification. The reality involves grinding wafers down until they're paper thin, adding in filler pieces and structural supports. It's less like stacking Legos and a whole lot more like making a super delicate multi-layered silicon sandwich. And understanding how that sandwich is made, that's the key to seeing where all of computing is headed.
So that is exactly what we are going to unpack in this explainer. We're going to peel back the layers on an absolutely incredible piece of packaging technology that is very quietly changing, well, everything.
To really get what's so new and exciting here, we first have to understand the old way of doing things. For decades, the way we've connected chips together has pretty much been the same, relying on a method that's been around since the 1960s.
It's called flip chip bonding, and it's basically what it sounds like. You put these tiny little balls of solder called C4 bumps, or even smaller micro bumps, on a chip, you flip it over, and you melt them to connect it to something else. It's reliable, it's been the standard forever, but those little solder balls have a physical size limit. They're the bottleneck. They're the reason you can't just stack things incredibly close together.
And this is where the new leap comes in. Instead of using solder, hybrid bonding is a completely different animal. It literally fuses the copper pads on two separate chips directly into one solid piece. You can think of it as welding silicon together at a microscopic level. It takes insane precision, but the payoff is huge.
And how huge is that payoff? We're talking about a 16-fold increase in the density of the connections compared to the old way. This isn't just a small step up, it's a massive jump that lets two chips talk to each other as if they were carved from a single piece of silicon.
The other massive benefit is energy efficiency. See, those shorter direct copper-to-copper connections have way less electrical resistance. We're talking about a 90% reduction compared to solder. That means it takes a lot less power to move data between the chips, which is, as you can imagine, absolutely critical for performance.
So how does this magic actually work? Well, first you get the surfaces of two wafers perfectly flat, with these tiny copper pads sitting just inside a dielectric material. Then, in a vacuum, they're aligned with incredible precision and pressed together. That forms an initial bond. After that, you add a little heat to strengthen that bond, and finally, as you heat it up more, the copper pads actually expand, they touch, and they fuse together, creating these perfect, seamless electrical connections.
Okay, so now that we get the technology, let's circle back and solve our original mystery. Let's apply what we know about hybrid bonding and figure out what that first-generation X3D chip really looks like under the hood.
Right, so here's the first big problem those marketing animations conveniently skip over. Silicon wafers are made to be pretty thick, for structural support. But to stack another chip right on top, all that extra bulk silicon on the back is just in the way. It has to be ground off in this super delicate process called wafer thinning.
So the real silicon sandwich starts at the bottom with the main CPU die, but this isn't a full thickness chip. No, it's been ground down until it is incredibly thin. Basically just the important stuff, the active transistors and metal layers.
Now, on top of that super thin CPU, you place the thinned V-cache die. But you can't just press it on because the cache die is actually smaller. And for this process to work, you need a perfectly flat surface, so you have to place two little filler pieces of blank silicon right next to it to even things out. And here it is, the secret ingredient, the part that's always left out of the animations. That combined stack of the CPU and the cache is now way too thin and fragile. So, a third layer, a totally brand new piece of plain structural silicon, is bonded on top of everything to provide rigidity and bring the whole package up to the standard height.
So when you put it all together, the first-gen X3D chip isn't a simple two-chip stack. It's a 5-piece sandwich. And this complex structure is the real reason for the thermal problems those early chips had. Heat from the CPU had to fight its way through multiple layers of oxide bonding, which are terrible at conducting heat, before it could ever get to your cooler.
Okay, so for Zen 5, AMD completely flipped the script. They put the cache on the bottom and the hot CPU die on top. Now, this seems like a pretty obvious fix for the heat problem, but it introduces a totally new and, you could argue, an even more complex engineering puzzle. So here's the trade-off. With the CPU on top, heat can get out easily. That's a huge win. But Now all the power for that power-hungry CPU and all its data connections have to travel through the cached chiplets sitting below it. And this requires a massive increase in the number of these little vertical connections called TSVs, adding a ton of routing complexity to the whole design.
This leaves us with two likely ways the new Zen 5X 3D chips are being built. One option is a clean 2-die stack, but what's probably happening, given just how hard all this is a 3-die stack that still needs a top layer of structural silicone for support. It's definitely a better thermal design than Gen 1, but it just goes to show how incredibly difficult this whole process really is.
So you might be asking yourself, why? Why would AMD go through all of this trouble? Why completely re-engineer such a complicated process for just one line of consumer gaming CPUs? Well, this is where we need to zoom out and look at the bigger picture.
The theory is this. Zen 5 X3D isn't just about making the world's fastest gaming CPU. It's a public test run. It's AMD and TSMC mastering this incredibly advanced packaging at a huge scale, getting ready for a future where everything is going to be stacked.
Just imagine what that future could look like. You could have a big base chip that integrates not just the cache, but all the I/O functions that currently need their own separate die. Then, you could use hybrid bonding to stack high-performance CPU cores right on top of it. This would create a super tightly integrated system with bandwidth and power efficiency on a scale we just haven't seen before.
So the next time you see a simple animation of chips being stacked, remember the real silicon sandwich. Remember the complex dance of bonding layers, filler silicon, and those hidden structural supports. The lessons being learned inside today's top gaming CPUs are building the foundation for all of computing tomorrow. And the question isn't if your devices will be built this way, but really, just how soon.